Section 4.4 is the rational root theorem. The rational root theorem will be explained down here below, but let me give you an example of how we're going to use it. Before, we learned how to factor something like this with a coefficient bigger than 1 in front of it, 3x squared plus 14x minus 24. Remember that we multiplied this 3 and this 24 together. Had to find these guys is, when you multiply those two, we get what, 72? We had to find the factors of 72 in order to figure out how to factor this thing, right? And it turns out, I believe, that 18 and 4 multiply to be 72, and if you were to make these, this means the signs are different. The bigger one is positive. That would add up to be 14. We could go about our process that way in order to factor it. What the rational root theorem is going to do is it's going to show us a different way to do it using synthetic division. Sometimes could be faster, depends on what you like, but regardless, I'm going to give you the option, and we're going to work on the rational root theorem. So the rational root theorem says that the roots of a polynomial will be one of the rational numbers made by the factors of the coefficients of the highest degree and the constant. So in this case, the highest degree is the one with that is an x squared. 2 is obviously bigger than the exponent here, which is 1, and bigger than the exponent here, which is 0, x to the 0 power. So the rational root theorem says the roots have to be made up of factors of the highest degree, so factors of this guy, and of the constant. All right, and the factors of the constant over the factors of the highest degree. So in this case, my factors of the highest degree are plus or minus 1 and plus or minus 3. The factors of 24 are plus or minus 1, plus or minus 2 times 12. And then I should have 24 down here as well. And then I have, what, 3 and 8. And I have 4 and 6. And those would be all my factors. And what that thing is saying is that all my options for roots for these guys is going to be everything that's going to be the factors of the constant divided by the factors of the highest degree. So we have 1 all over 1, negative 1 all over 1, negative 1 over negative 1, stuff like that. So these are all our options, and what we'll end up doing is using synthetic division in order to find the roots for certain equations. A lot of times this comes in handy when we're not dealing with something that's squared and we don't really know how to factor it, such as this guy right here. So the possible factors, the possible roots of these guys are going to be the factors of the highest one and the constant. So the factors of my highest one is 1 and 2, all right? And the factors for 25 are 1, 5, and 25. So my possible factors would be, let's see, 1 all over 1, so 1 plus or minus 1. 1 over 2, so plus or minus 1/2. And then 5 over 1, so plus or minus 5. 5 over 2, so plus or minus 5/2. And then 25 over 1, so plus or minus 25. And 25 over 2, so plus or minus 25/2. So those are all our options for possible roots. And to figure out whether it's a root or not, we do synthetic division. If it's a 0, then it's going to be a root. So something that comes off that is called the integral root theorem. It says if the leading coefficient is 1, then the root must be a factor of the constant. So in this case, the leading coefficient, this guy, the leading coefficient is the number in front of the highest degree. So in this case, this number here, if that is 1, it has to be a factor of this guy. So that narrows it down quite a bit for us. So we know in case here, in this case right here, that one of the roots has to be a factor of 3. So it's either going to be 1, because that 1 times 3. So it's either going to be positive 1, negative 1, positive 3, or negative 3, which makes sense. It's the same thing as the rational root theorem up above, because if this guy's factors is just 1, so we went 1 all over 1, 3 over 1. So anyway, let's continue then, and let's find the roots of this guy right here. So what I have now, I'm going to write my synthetic division. I know it has to be plus or minus 1 or plus or minus 3. And let's write it in synthetic division. Let's see here. 1, 6, 10, and 3. I'm not missing any powers of x's. And then let's do our synthetic division. If I get 0, then we know it's going to be a root, right? So if I plug 1 in here, drop my first one down 1. This would be 1. This would be 7 because I add down, and this would be 7, and this would be 17. That one's not going to work. So one is not a root. One's not going to work for us. So let's go ahead and let's try, I don't know, 3 or -3 or -1. I don't know. Let's try 1, 6, 10, and 3. Let's try negative. Let's try -1. So if I pick -1, drop the 1 down, 1. This would be -1. This would be 5. This would be -5. This would be 5. This one, -1's not going to work either. So hopefully 3 works. 3 or -3. Let's try -3. Let's try -3. So drop my 1 down, 1. This will be -3. This will be, let's see, 3. And this will be, let's see, -9. This will be 1. This will be -3. Hey, we found one. All right. So we know that that's going to be a root. If we were looking to factor this thing, one of the factors then would be x plus 3, because we know that when we synthetically divide, this is opposite of what our factor was above. That's a root. We could continue going, or we could say, all right, well, this is saying x squared because it has to be 1 degree less. X squared plus 3x plus 1 is what's remaining. And if we could try to factor that out as well. And it looks like we're not going to be able to factor that easily. So if we kept going and tried -3, it wouldn't work. 3 and all that stuff wouldn't work. So we found a root right here. In that case, to be our answer. So -3 was our answer. So why don't you go ahead and give that one a try in your own notes. And then in your notes, I want you to think and write down everything you can do to help you graph a function and how you do those things. For example, we've learned how to find roots, which are the x-intercepts. You know how to find the y-intercepts. You know that you can take the derivative, which is going to tell you whether it's increasing or decreasing on a certain interval. It's going to tell you critical points. Go ahead, think through. You also know your axis of symmetry if it's a quadratic function, stuff like that. Go ahead, look through your notes, think of that, put it all together on one page so you have it in one place, and label it things to help you graph, stuff like that, and what it does for you. That'll help you organize what we've been doing so far this trimester. All right. The next thing to talk about is called Descartes' rule of signs. And Descartes' rule of signs says if the polynomial's terms are arranged in descending order, so that's what we want. We want to arrange in descending order. Then the number of positive real zeros, so now number of positive real zeros, zeros that we can graph, zeros that we'll get factors of, is the same as the number of changes in signs of the coefficients. So I'll give you an example down below, but here is one example, x minus 2. This is a positive, this is a negative, that's one change of signs. So the positive real roots is going to be the same as the number of sign changes, or less than that by an even number. So say that we have 4 sign changes, we could have 4 real roots, or 2 real roots, or 0 real roots, all right? So, and then in 2 here, it says the number of negative real zeros of the polynomial is the same as the number of changes in sign after we plug in -x for x and rewrite the equation, or less than that by an even number. And I'll go through an example here to illustrate that. It says state the number of possible complex zeros, the number of positive real zeros, and the number of possible negative real zeros. All right, so we know that total there are 4 possible complex zeros. We learned that a couple sections ago, saying that the number of complex zeros is the same as the highest degree of your equation. All right, so we know that there's 4 possible complex zeros right here. Okay, to find the number of positive real zeros, what we're going to do is we're going to look at how many sign changes we have. We have a positive to a negative. That's one sign change. All right, positive to a negative. Now we have a negative to a positive. That's 2 sign changes. So there's 1 sign change, 2 sign change. Then we stay from a positive to a positive. That is not a sign change. And then we go from a positive to a negative. That is a sign change. So what it's saying is we can have 3 or 1, because it says or less than that by an even power, by an even number. 3 or 1 positive real roots. All right, so that's good. We know at least we're going to have one real positive root and maybe even three. And they said look for the number of positive negative real zeros. So in order to find that, our notes said that we were going to plug in negative x for x, and we were going to rewrite. So negative x to the fourth minus 2 times negative x cubed plus 7 times negative x squared plus 4 times negative x minus 15. And then let's rewrite this, because anything to an even power is going to be positive. So this becomes x to the fourth power. Anything to an odd power is going to stay negative. So I have a negative x times negative 2, which is going to be a positive 2x cubed. And now, again, this one's going to change to be positive. I don't know why I put the squared on the inside. It should have been on the outside. But this is going to be a positive, so it's going to remain plus 7x squared. I have a positive times a negative, which should end up being a negative 4x, and then a negative 15. So after we rewrite, now we check out the number of sign changes that we're going to have. This is a positive yet. This is a positive, no sign change. This is a positive, no sign change. This is a negative, so there's one sign change. And this is still negative. So we know for sure that there's going to be one negative real root for this equation right here. The reason why we do that is so it's helpful. Now that's going to tell us that we are going to have at least two, at the very least, two roots, one positive and one negative. All right. So it just helps us know, it helps us pick from the rational root theorem on what numbers to pick. Are we going to pick positive numbers, negative numbers, and stuff like that? All right. It says find the zeros of this function, then graph the function. Okay, so to find the zeros, first of all, let's look at the sign changes, see what kind of zeros we're going to have here. So I have no sign change, no sign change, one sign change here. So I'm going to have one positive root. All right, and how many negative roots am I going to have? Well, let's plug in negative and rewrite the thing. Was this the same? No, it's not the same as the one previously. So we're going to have, let's see, negative x. If I plug in negative x, I have negative x to the fourth plus 4x. Sorry, that should be negative x. So plus 4 times negative x cubed plus 3 times negative x squared minus 4 times negative x minus 4. And rewrite to see how many negative roots we're going to have. This is going to be a positive x to the fourth. Then this is going to be still a negative, so minus 4x cubed. This is still going to be a positive, so plus 3x squared. This will turn into a positive. Negative times a negative is a positive, so plus 4x and then minus 4. How many sign changes do we have then? We have one sign change here, two sign changes. This one is the same, no sign change there. Three sign changes, so we're going to have 3 or 1 negative roots. All right, so that's going to help us in our decision process on what to pick for our options for our roots here. So we have one positive one and 3 or 1 negative ones. All right, so let's find its roots. So we're going to find its roots by synthetic division, and our choices to divide by are going to be the factors of my constant and the factors of the number in front of the x, which just in case is 1. All right, so my choices are here are 1 and 4, and 2 times 2 is going to make 4. So my choices are plus or minus 1, plus or minus 2, plus or minus 4. All right. So let's go ahead and write our synthetic division out. We're going to have 1, 4, 3, 4, and 4. And negative 4, sorry. This is going to be negative 4. This is going to be negative 4. And other than that, my signs are okay. And let's go ahead and choose something. I have a bigger probability maybe of picking a negative one. Maybe there's 3 of them. I don't know. Let's try negative 1. Try negative 1. So bring down my first term. That's going to be negative 1. This is going to be 3. This is going to be negative 3. This will be 0. So this will be 0. This will be negative 4. This will be a positive 4, which is 0. Hey, that's awesome. All right, so negative 1 is a root. We know we're going to have an intercept at negative 1. All right, so what we can do, instead of trying and redoing all this stuff, we can just go straight here from this depressed polynomial and try something else. Try one of these guys. I don't know. We know negative 1 already is. Let's try -2. Maybe we have 3. Well, we know we're going to have one positive root, so maybe we'll try 1. I don't know. Try 1. Drop our 1 down. 1, that's 4. 4 times 1 is 4. Add these down, that's still 4. Add this, that's now 0. So hey, good. We have a root at 1. That's also 1. A root at 1 as well. Okay. So we can continue going on this. And I don't know, since we already have our positive one, so picking positive numbers is kind of out of it. So let's pick, I don't know, we haven't tried -2 yet. Maybe -2 will work. I'm completely guessing this. I have no idea. I haven't looked at any of this. So 1, multiply 1 and -2, and I get -2. Add those down, I get 2. -2 times 2 is a -4. Hey, that's also a root as well. So since we have at least 2 negative roots, we're going to have 3 negative roots. That's what it tells us. We can't have 2. 2 is not an option. So I'm going to have a root at -2 as well. All right. And then the last thing to do, when we get to this point, we can just write. We know we keep depressing the polynomial. Well, when there's 2 things left, it started out at x to the 4, so this guy's got to be x to the 3rd. This one's x squared. This one's just x. When we're down to this point, we can just say x plus 2 equals 0. And there's going to be another root at x equal to be -2. Okay. So there's a lot of things that we've talked about in graphing. One of them is end behavior. If you think about what the end behavior of this graph is, you know that it's a x to the 4th graph. So you know that it's going to be a parabola from your parent graphs. You know it's going to be something like this, and it's going to be doing something crazy in the middle. And we're not sure yet what it's going to do, but we know that the end behaviors have to end up like that. That's one option. So it's going to have to come down like this at some point, and it touches right there at -2. Another thing we do, we could find the derivative and find out where our critical points are. Or what we could do is anytime we have a double root at -2, that means normally it's just going to come down and touch at that double root. Did you notice that -2 showed up twice? So when we have a double root, it's normally going to come up and it's going to touch it and it's going to come back up. And then it'll go down. And we know that it has to come up. And it's going to be something like that for our graph. And if we're just sketching it, I'm okay with that. If we wanted an actual graph, we could plug in points. Like here, I know, I guess I could have plugged in my y-intercept and we could have gotten -4. So this really should have went down 1, 2, 3, 4. It really should have went down here. I messed up there. So it really should have came way down here. Then we know it, since it has to cross, it has a root right here. It has to cross right there. We know the end behavior of it has to be a parabola and stuff like that. So normally the biggest thing is when we had a negative. I wish I wanted to delete that, because we had a root that ended up showing up twice. X equals -2 was a root twice at the very end, and we picked it at the end and we picked it earlier. So normally when you have a double root, that means it's just going to come touch it and then it's going to come back up. So another way to tell that is you could also find your critical points, and you could also take the derivative and see if it's increasing or decreasing in this interval and all that stuff to see whether it continues going up or maybe it goes down. So you have a bunch of tools at your disposal to use, and that's why I had you write that page of notes earlier. So that's all I have for you. I hope this helps. See you in class.